Okay, so now let's start with something a bit more difficult. We're moving on to some more complicated image manipulations and transformations. And we're starting with some simple ones, which are translations and rotations. So let's take a look at what they actually are. So firstly, transformations are geometric distortions enacted upon an image. And what exactly does that mean? Well, they're used to correct distortions or perspective issues arising from the point of view of the image was captured. And two main examples are affine and non-affine. Now, I'm pretty sure you're confused. However, this diagram should shed a bit more light onto what transformations actually are. Imagine this is our original image, and we're doing some operation on it to move it this way and then move it that way. That is the simplest type of transformation, and that's called a translation, which you will see in the following slides. But for now, let's take a look at what affine transformations actually are. So take a look at these objects here. Let's start with this one right here. Firstly, you can see scaling. Now, intuitively, you know what scaling is. It's making something larger or bigger. So it's an operation that changes the size of an image. And you can see just a square, a larger square here, and a smaller square here. Now, let's take a look at rotations. It's the same square, but now it's tilted in this direction. We went anti-clockwise a bit. And look, this is the square, remains same shape and size, however, it's now tilted. And translations, which we mentioned before, is the same square here, but now it's shifted. Now, the square remains here, by the way. You just shifted off my canvas of my page here, just to illustrate what happens when you translate or move objects in an image off of the canvas. Canvas being the image pixels or image dimension in pixels right here. So that's what a translation is. And also we have skewing. Now, skewing is a bit more complicated to understand, and it's also called shearing. However, it's just transforming. So what's happening in skewing, essentially, which it's a bit tricky to explain here, but every point on the image here is being mapped to a predefined other point here. However, that isn't simply what it is. And this becomes the essence of what affine transformations actually are. Take a look at the lines in this skewed squared. These two lines are still parallel, just like they were here. And these two lines were parallel here. In affine transformations, parallelism is maintained. And you can see in all of these other transformations here, parallel lines will remain parallel. Now, there's a lot more maths you can actually do to apply this and understand this better. However, for your knowledge and your sake right now, these are what affine transformations actually are. Just remember they preserve collinearity and parallelism, okay? Alright, so now let's move on to non-affine transformations, or also called projective transforms and also called homography as well. So in non-affine transformations, what happens is that we don't preserve parallelism, length, and angle. It does, however, preserve collinearity and incidence. Collinearity meaning that the points still lie on a straight line, so we're not actually like bending points along. So imagine this line is still a line here. We're not actually warping this line, essentially. However, you can see, though, that we've lost parallelism in these two lines here, this line and now this line. So that proves that this is a non-affine transformation. So now let's move on to something simpler. Okay, so don't get confused with this translation matrix here. I'm going to explain to you what this is exactly, okay? So now translations, like I said before, are simply shifting an image left, right, up, down, okay? Now, how do we shift and how do we do this? Firstly, we need to define a translation matrix here. So what we do, these are the parameters we leave here. We leave these ones and zeros here, and we have this tx and this ty. So what exactly is this? Well, this tx and ty are how much we move the image, we shift the image in the x-axis direction or the y-axis direction. So you can see, let's just assume this was say 100 pixels and this was 100 pixels. It pushes the image now from here, remember its starting point right here, shifts it to somewhere down here, which is how this image looks like this now. And if you're curious about how the translation matrix actually enforces this image or this shift, imagine we have an x and y coordinate here, all right? If you're familiar with matrix calculations, it's going to be very easy for you. If not, I'm not going to go through the math in detail, but what I'm going to tell you is that you take the coordinates of a point. Let's say we're taking this point here. Well, let's assume this point is 1, 1 instead of 0, 0. When you multiply 1, 1 by this matrix here, and tx and ty are how much we're going to shift the image by, let's say 100, you're going to get the new coordinates as the output, as the result of that multiplication. And that's how we use translation matrix to get the new points here. That's mathematically how it's done. All right, so now let's take a look at rotations. Now rotations have a different matrix here. You have all these cosines and sines here. So what a rotation does now, take a look at the image here. Before I go into the OpenCV function, what I'm going to show you here is, imagine we have this image right here. And we want to rotate this image by theta degrees in the anti-clockwise direction. So what we do, we again take all the coordinate points here, multiply it by this matrix here, where theta is the angle we want to rotate it by, and this is a resultant image. And using the CV2 get rotation matrix 2D function, you have the inputs here. And now pay attention to what the inputs are. Rotation center X and rotation center Y, the angle of the rotation, and the scale. So let's ignore scale for now. We're assuming a 1-to-1 ratio with scale here. Now the rotation center is point we're rotating about. You can rotate about any point. You can rotate about this point, and the image is going to swing all the way over here around this point. Imagine this point being a pivot, and any pixel here can be a pivot. Now typically we assume the center of the image is always the pivot. However, that's not entirely true. If you've used apps or Photoshop, you can always drag the center around and rotate around that point. It's quite cool. And basically this is how the function fit is done. So this CV2 function here just takes these inputs here and does the rotation for you, okay? By doing the mathematics here, by just multiplying every pixel by this point to get a resultant output pixel. So now let's actually do this and perform these operations in OpenCV. Okay, so let's begin with our practical portion of that section, which is the translation and rotations we're actually going to perform using OpenCV in Python. So let's open this file here. That's file number 4, transformations here. All right, now there we go. So the first thing we're going to introduce to you is the warp affine CV2 function, okay? So what that function does, that function is quite simple in that it takes our matrices here. It's one single matrix, and create it here in code. I'm skipping some bits here because I'm going into the core of the code right here. So you've seen these bits before, I'm sure. And now what we do here, we take the CV2 warp affine function. We have the image, we put the input translation matrix here, and basically we do width and the height. Now the width and the height is something that you don't actually need to think much about because it's the end shape. It's basically like a scaling factor here. So we're just going to put the image back in the same width and same height as we had before, okay? So just to go through this here, we get the width and the height of the image by using the shape function, which is a NumPy function, which you've seen before. And what we do here, we're just going to shift it by quarter of the height and width. So we just simply divide height and width by 4 to get quarter height and quarter width. And then we shift it, we put Tx and Ty to be quarter height and quarter width, which is how we have this translation matrix here. And there we go. That's pretty much it. So let's take a look at it. So this is exactly what we expected. We shifted the image in this direction here. Just imagine an arrow pointing that way by quarter of the height, which is this width dimension here, quarter of the width, which is this dimension here. So that's simply all we did. So if you want to take a look at what T is, I already have the output printed, but we can do it again. This is what quarter height and quarter width was. Okay, so that's our translation matrix here. So now let's move on to rotation. So remember in rotations, the CV2 get rotation matrix 2D, we have the rotation center, X and Y coordinates, the angle of rotation, and the scale of the final image. All right, so now let's actually do this. So we are going to get the center of the image, first of all, which is a pivot point we're rotating about. It's just simply the width divided by 2 and the height divided by 2. 90 degrees, which means we're going to flip it anti-clockwise, exactly 90 degrees. And we're going to reduce the scale to 0.5. So let's take a look at how that is done. And just so you know, there's an extra step here, because what this does here, this CV2, that rotation matrix here, is exactly that. It gets the rotation matrix. And then we input this rotation matrix into warp affine right here. Just like we did before with our translation matrix T, we have our rotation matrix here. And we just do this and rotates around the center here at 0.5 scale, so you can actually see the entire image here without it being clipped. Because let's take a look at what happens if we didn't do this scaling here. So let's put it at 1. You see, the ends are clipped. So let's keep it at 0.5. Now using the rotation matrix with warp affine allows for a lot of powerful rotations where we can actually control the angle of rotation, the final size, everything. However, what if we wanted to do a simple rotation and not have all that black space around the image? And the black space I'm referring to is this, because this happens because of the scaling we've used and how we've rotated the image around the existing canvas. So what if we just wanted our simple rotated image without all this black borders here? So let's take a look at how we do that. And we can do that by simply taking advantage of the CV2 transpose function. Now, if you're familiar with matrices, a transpose function basically flips the matrix over its diagonal. So imagine we have a matrix where, let me see if I can actually describe this properly. Let us put like 1, 2, 3, 4, 5, 6. And if we were to transpose this, what happens? We end up with, let's just do it here. It's an equal sign, it equates to, and we have 1, 3, 5, like that. And we have the final one, which is 2, 4, 6. All right. That is effectively what transposing this matrix does. Okay. So what we do by taking advantage of the transpose function here, we're going to actually flip this counterclockwise like this. And as we're transforming pixels directly, we don't end up with any black space around it. It actually just rotates the image around a 90-degree angle. Okay. So that's fine. Now, what about using flip? Now, what does flip do? Let's try something here. This is our image here. Now, did you remember the original image? Probably should have kept the original image up. So let's actually do that. Let's do some good practical work here. So let's take the original image here and let's call this original. So now you can actually see what the flip did. And actually, I can put it like that and you can see it's like a mirror image here where just everything that was on this side now is on the right. So that's what flip does. And we can actually do a different argument in flip. We can have -1 and it flips around the vertical axis here. Okay. If you want to picture it better, you can just align it like this. Might not fit if totally. Bring this down a bit and there we go. So you can actually see the mirror image flip, vertical flip there. So -1 gives a vertical flip and +1 gives a horizontal flip like this. Which you should have left it like this initially, but there we go. Okay. And this is actually the original here. So this should actually be on the left and this should be on the right. So you can actually see the line that it basically flips from, this center line here. Okay. There we go. So that concludes this lesson right now. So what have we learned in this lesson? Well, we've learned how to perform translations and rotations in OpenCV using CV2 Warp Affine and CV2 got rotation matrix, and that's to get the rotation matrix, which we then feed into Warp Affine to get the final transformed image. And then we also learned how to use CV2 transpose to do quick counterclockwise rotations where we eliminate the black border, and how to use CV2 flip to actually flip images around the horizontal or vertical axis. So now that concludes this video. And now let's move on to scaling, resizing, interpolations, and cropping. Okay, so stay tuned for the next video. Thank you.